Welcome back to The Explainer. Today, we're talking about something invisible, but it's a force that powers pretty much everything around you. I mean, it's the quiet, spinning heart of our modern world, and you've probably used it like a dozen times already this morning without even thinking about it.
Yep, we're talking about the electric motor. It's this incredible unsung hero tucked away inside, well, everything. Your toothbrush, the fridge, your car. It's the engine that literally makes our world go round.
So, to really get what makes any motor tech, we've got to break it down. It really just comes down to two key parts and this powerful, invisible force that makes them dance.
And here's the cool part. It's not some super complicated engineering magic with a million gears. Nope. At its very core, every single electric motor runs on a principle you definitely learned about in science class: plain old magnetism.
Okay, so first up is the stator. You can think of the stator as the motor's anchor. It's the part that stays put, completely fixed in place. Its one and only job is to generate a really strong, stable magnetic field. And then, reacting to that magnetic field, you've got the rotor. This is the star of the show, the part that actually does the spinning. It's constantly getting pushed and pulled around by the magnetic forces coming from that stator. So here's where the magic really happens. The stator sets up this kind of magnetic dance floor, and the rotor is basically designed to chase after it in a never-ending circle. It's this constant push and pull that creates what we call torque, and torque is just that rotational force that makes things, spin. All right, so we've got the basic idea down, right? Stator, rotor, magnetism. Now, let's get into the two main families of electric motors. The big difference between them is the type of electricity they eat. AC, or alternating current, and DC, direct current. And this chart breaks it down really nicely. You've got your AC motors. They're the ones that run on the power coming from your wall outlets. Think of them as the simple, super reliable workhorses. Then you have DC motors. They're all about precision and control. They're what you find in battery-powered devices, and they give you amazing control over speed and power. Okay, let's dive into the AC motor family first. These are, by far, the most common type of motor out there. Why? Well, because our whole power grid runs on alternating current, so it just makes sense that these motors are absolutely everywhere. First up, in the AC family, we have the synchronous motor. This thing is a master of precision. It's all about perfect timing. So what makes it so special? Well, its speed isn't just kind of fast or kind of slow. It's perfectly, and I mean perfectly, locked to the frequency of the power coming from the wall. So on a 60 hertz line, it's going to spin at a very specific speed. It's like a metronome, always ticking at a constant, predictable rate. And because of that perfect timing, they're the go-to for jobs where everything has to be perfectly in sync. Think about old electric clocks that never lost a second, or a huge factory assembly line where every single belt and robot arm has to move in perfect harmony. That's a job for a synchronous motor. All right, next up, we have the undisputed champion, the heavyweight workhorse of the entire motor world, the AC induction motor. These things are simple, they're tough, and they are everywhere. The design is just brilliant. Honestly, you can think of it like wireless power, but for motion. The stator's magnetic field actually induces a current in the rotor without ever touching it. There are no brushes, no physical connections. And that means there are way fewer parts that can wear out or break. And because they're so ridiculously reliable and cheap to build, these are the motors that are quietly humming away all over your house right now. You know that steady hum from your fridge? Or the whirring of your washing machine? Yep, that's the sound of an AC induction motor, just doing its thing 24/7. Okay, let's switch gears, pun intended, and talk about the other side of the family, DC motors. And if AC motors are the workhorses, DC motors are the precision artists. The big thing to remember about DC motors is one word: control. It's all about control. By tweaking the voltage you feed them, you get incredible, fine-tuned command over both their speed and their torque, how much power they're putting out. A great example is the Series DC motor. Because of how it's wired up inside, it has a superpower, ridiculous starting strength. I'm talking about the ability to generate a massive amount of torque right from 0 RPM. And that raw, get-up-and-go power makes it the only real choice for jobs that need to move incredibly heavy things from a dead stop. We're talking trains, the starter motor in your car, massive industrial cranes and hoists.
Okay, but what about smaller stuff? For that, you've got the really slick permanent magnet DC motor, or PM motor. It's a clever design that gets rid of the power-hungry coils for the field and just uses strong permanent magnets instead. This makes them way more efficient and perfect for smaller, often battery-powered devices.
And finally, we've got to talk about a real specialist, a type of motor that is absolutely essential to our modern digital world. This is the stepper motor, and its name tells you everything you need to know. It doesn't just spin freely like the others. Nope, it moves in precise, individual, highly controlled steps.
So how does it do that? Well, a computer controller sends a pulse of electricity to one set of coils in the stator, which pulls the rotor to a very specific position. Click, that's one step. Then the controller energizes the next set of coils, and the rotor moves to the next position. Click. It's like watching the second hand on a watch, moving with perfect digital precision. This is the magic behind things like 3D printers and robots, where exact positioning is everything.
So, when you think about it, from the massive motors that drive our industries to the microscopic ones that will probably build things for us in the future, it all comes back to that simple dance of magnetism we talked about. It's not just about how things work, it's about what we can make them do. It really makes you wonder, right? What are these invisible engines going to make possible next?